And it's also taken an problem. Somehow an application comes up like this, people actually go back and redo a lot of maths. So that also happens. There's a famous book by Roy and Meester called Continuum Calculation. So this book was published before this paper. So typically the book says like this and then they just fade out. Because of this 2000 paper, suddenly it skyrocketed, just because of this paper. So the whole community wanted to look at it. So this book was a ready reference for what they were doing. So this is a beautiful book. So Roy in ISI, very Easter is somewhere in UK. Okay, so what are we going to do? We're going to still, the model is not very different. I'm just going to define something and start counting. N points, so this is my unit square. N points are uniformly distributed. So N points. Uniform distributed. Yes. So earlier what we did do was we just connected these 2 points as long as, so let's say x and y. There was an edge on x to y. S side and x to y. So that's what the graph we construct. Now we're going to look at a more network view. So x is my source. And its destination is one of these points uniformly randomly chosen. So among the n-1 points, pick any one uniformly randomly. Let's say that's my. And this is done for everybody in the understand. For every node here, pick uniformly randomly. So you will get n by 2 pairs. And what you want to do is to communicate from this source, let's call it source 1, to destination 1. Similarly, there is S2, let's say B2, and so on. So many n by 2 pairs which are trying to communicate simultaneously. What you want to find out is what is the highest rate of communication across the network. The total number of bits you can transport through this network. That's what you really want to count. And that's why the paper title was capacity of wireless network. It's a capacity in terms of bit carrying capacity. Because as you can predict, from transmitting here is going to preclude somebody else from transmitting. Because of my SIR. So per hop, I'm still going to worry that a communication is successful at a particular rate if there is an edge between these 2 points. But that's not sufficient because the destination will be far away. So I might have to reroute data like this, in which case other things have to stop possibly. So what are we trying to find? That at the same time, so essentially think of 1 hertz of bandwidth, because otherwise you can always multiply with the bandwidth. So bits per second per hertz. So think of at the same time, the same frequency, how many bits I can push through this network is what I'm interested in. And an edge exists between 2 nodes only if SIR between them is greater than beta. And if this is true, the rate of communication is the same notation, just a function of beta. B of. So higher threshold I demand, larger is the rate at which I can transfer. But if I increase beta, so this is an increasing function of beta. But if I increase beta, the number of edges will go down. So there's a trade-off. You can demand a larger beta, but at the same time, the edges will exist with less probability. But if it does exist, then amount of rate pushing through will be higher. So we're not going to play with beta for this. You will also play with beta. If it's a beta, you get that much rate. All I want to count is through this network, how much I can push through simultaneously. So is the broad idea clear? I'll define everything rigorously.
We want to see how many pairs are connected.
Not necessarily. See, pairs, the problem is if the rate of communication goes down to zero, everybody is connected. What I'm interested in, how many bits can you push through this network per unit time? If that is zero, everybody is connected. But the rate is zero, right? So that's not good enough. It's what you're saying is involved inside it, that how many connections can coexist. But that's not necessarily I'm counting. I'm counting the total amount of bits I can push through this network, which is counted by this. So this is the bits over one particular edge, if the line between them is greater than beta. That's the rate at which per link communications happen. So if you will think about one single source and one single destination, if it's edge hops away, what is the rate of communication? If it was edge hops away, it's not necessary that the source is directly connected with this mesh. It could be that I'm actually going to route traffic. So supposing I'm using edge hops, what is my rate of communication? Does it come down by edge or it's independent of edge?
It should be inversely proportional.
What?
There could be some noise or disturbances that might occur due to the distance.
No, so per link, I'm able to communicate. It's just that there are edge hops. That's all.
Will be constant by that.
Okay, so either of the two is correct.
No, the first bit would take time, but
Pipelining is okay. So you're not going to bother. You're not going to bother about the setup. But once it starts, it's very explorer. I don't care how many hops there are. I'm not counting that what is the probability that it fails on at least one of the hops. That would increase. But supposing I have edge hops can simultaneously work, the throughput doesn't suffer. No, what else can be observed directly? So as n increases, what do you expect? See, all we are asking for is scaling results. We're not asking for numbers. As n increases, how do you think the throughput is going to improve? It's called for throughput capacity. Do you think it will increase with n, decrease with n, remain constant? That is something intuition we should be able to generate. So as n increases, what is happening to the network? The demands are increasing, right? Because all n by 2 pairs have to essentially communicate. So if the overall capacity is not going to scale linearly with n, the per source destination capacity is going to go to zero with whatever rate possible. Is that clear?
no.
So suppose the overall capacity of this network does not scale linearly with n. Suppose it is square root n. What is happening to the per source destination pair? There are n of them. The overall capacity will be square root n. So each one gets only 1 by square root. So per source destination pair is actually going down. So overall it might be increasing. But does even the overall thing increase, or that itself goes down? Overall itself. See, there are two effects happening at the same time. As it increases, the distance is also shrinking. It's just that there are more requirements for each source destination flow. So there are network effects and there are local effects. I increase this, the distance between these points is actually changing. Right? But if you randomly pick a source and destination, that distance remains the same, order-wise. So per source, then the source destination demands are becoming harder. But as a network, possibly I can actually increase because the distances are becoming smaller. So there are all sorts of things which can happen. It's not an obvious answer that this should happen. I'm going to go ahead and prove it. So there are network effects and then there are like particular source destination pair effects. So as n increase, there's something interesting there. The network is getting closer and closer to each other. So you will expect more and more edges to form potentially. But at the same time, it might be that if you concentrate on one source destination pair, it becomes harder for him to communicate because there are so many others also who are part of the problem. Because as n increases, there are n by 2 pairs. Yeah. So this is the SRR model. This is another model called the protocol. They're all connected to each other. So suppose xi is transmitted to xj. It is successful as long as there is no other transmitter. So around this, so this is the receiver. So, these are the things that I'm drawing some radius. Xg. You take delta greater than 0. You draw a circle with radius for plus delta times xi. Okay. So this is my receiver. The receiver can actually get successful communication xi if in this circle there is no other transmitter. It's simply a guard zone. Essentially a guard zone. If there is another transmitter which is here, that's okay. If there is another transmitter trying to communicate to somebody else, its power here is going to be large enough, causing a lot of interference, and the connection will not work. So that's what this means. So if successful along with no transmitter. Yes. That's dead. Internet. These are the two communication models. One is the SILA model. So essentially, you are just defining an edge to exist. If this is true, earlier we defined an edge to exist with the SILA model. Both of them have connection to each other. Can you tell me what is the connection between the two? One is telling you spatial separation, other is telling you a SILA separation. What is the connection between the two? Here, essentially, bounding the interference. The interference has to come from necessarily outside of this. So nodes are outside, precisely outside of this particular disk. So the interference is controlled in some sense. So SINR is also controlled. The interference are not too close to you. So the signal power compared to the interference power is actually higher. Precisely, we'll see what that is. But it's intuitively you should understand that interference is only coming from nodes which are lying outside of the disk. So the signal power is a higher level compared to any one individual interpreter. It's not necessarily the sum of the interpreters is not sufficiently, but at least there is some control over from where the interference is coming from. Hopefully, this will be bounded. See, all of this, we are taking refuge in the fact that certain infinite series are bounded. That's what we are taking refuge in. If you go to a high school student, say sum 1 by n square, maybe earlier than high school, there is a infinite sum should go to infinite. Right? But the fact that that's not true is what precisely what we're trying to do. So if they're separate is sufficiently far apart, we're taking refuge in convergence of this. So as long as this is the constant, the interference is constant, I can get mine. That's precisely what we did in the earlier computation. We made sure that the coloring strategy was such that the nearest interferer was sufficiently far. And then I can count as many as I want. The lower bound is the more important. All right, so let me define
In this, what if X is also a transmitter? Then
XI is transmitted to XJ. That's what the real is. XI is transmitted to XJ.
X, now X is also a transmitter. Then
So at the same time, they're all transmitted to receive. You can allow that, but it's at any one point of time, either it's a receiver or transmitter. Because
but then you can't form these paths right in the graph.
no, so in a particular time, it receives, stores, and forwards. That's how a path is. Or you can think of it is that it can simultaneously transmit, but at a different frequency. Then it doesn't interfere with itself. I'm not going to there are a lot of work in that as well, but let's stay out of it. So at this point, we can really think of that data comes from XI to XJ, it's stored in that particular time, and then it's going to forward it later. Whenever it finds a path towards the rest. Okay. So that's node can really think of data right of T of n bits per second. Is easy. This shielding strategy such that each source network wide it will be n times defining per node. So across the network will be n times T. Okay, so now what we are interested in is what is the largest possible value of Tn and how do we actually end up achieving it? As usual, upper bound, lower bound. All right, so now think of a lower. That what you cannot do. Now we're interested in upper bound. Irrespective of whatever strategy you use, you should not be able to reach that. What do you think you can?
Are we doing XLR or protocol?
Either one. They're both connected. So one answer is actually valid for both. Because one implies the other. So at this point, I just want you to think about the intuition. What exactly is going on? What controls T of n? How many silent, or think about the following. How many simultaneous successful transmissions can happen in this network? That itself is a good idea. Remember, it's a bounded silent network. They're working with S1. The SIM model or the protocol model. What does it mean to have a particular edge? Essentially, it's including certain area to have some other transmitter. That's all it's really doing. Protocol model is explicit. If I'm transmitting to somebody here, there can't be anybody else in this part who can be also transmitted at the same time. So can you just make a simple geometric argument to say how large possibility of an will be, or how many simultaneous transmissions can happen at the same time? So that is for achievability. Here we are talking about what is not possible. So this has to be across all possible strategies.
All possible.
Strategies. We have, I don't know, unlimited number of strategies with which to achieve as high a T of n as possible. For the moment we are interested in, no matter what you do, T of n cannot be larger than this. So that has to be a strategy agnostic. So all I'm asking you to think about is just think of a geometric argument. But if each transmission is going to consume a certain area and the total area is bounded, what can you say about simultaneously active transmissions?
There are 8 by 2 pairs. Maybe 1 by 5 fractions that can be feasible. Almost. So for each edge you get a circle of radius 5 square.
Yes. But what is that R? That's the principle. See, this is not a Gilbert's model. But it's telling you something. How much in the protocol model, how much area was precluded? So if Xi and Xj are transmitting, it tells you exactly 1 plus delta. So the circle with 1 plus delta times Xi minus Xj radius. There can't be any other communication. So there is no fixed R. You have to slightly work with that. But do a back of the envelope calculation. Suppose I'm only transmitting to my nearest neighbor. How many such transmissions can I have at the same time?
Units square.
Yeah.
Distance would be 1 by square root n.
Okay. Is it clear what is the limitation of this system? There is so much physical area. Each communication is using up a finite amount of area. So how many communicate? How many simultaneous things are possible? That's all the simple matter. So what does each transmission consume? The total area is 1. So each successful transmission has to consume certain amount of area. How much is that? That's the question. So let's worry about the protocol model. I'll connect if I have a protocol thereafter. So we'll call. So let's set it. Okay. So square is the receiver and circle is the transmitter. X, 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 scale. Yeah. So what kind of inequalities can you write if communication between Xi and Xj has been successful? Just in terms of Xi, Xj, Xk, Xl. So where can XL be or XK be?
It's assuming Xj itself should be greater than size.
No, the communication content consider that Xi to Xk can happen only if Xk minus Xj is greater than delta. That's my starting point. That is by definition.
Excel should also satisfy that.
Why Excel is not transmitting? Why should I care about?
Means Xi is transmitting.
Yes. Xk is transmitting. No. If I'm not even transmitting, I can be anywhere.
I thought there's circle is transmitting. Excel.
No, I made a square there. That is confusing me. This is all I have. What more can you say? So can you give me an inequality between XL and XJ, distance between them?
Position of Excel.
So give me an inequality. In terms of XK and XL and XI and XG. Can you give me a lower bound on that? That will tell me how far any two receiving nodes can be. So I'm interested in writing a lower bound on Excel minus XJ. And remember, both are successful again. XK to XL is successful as well as XI to XJ is successful. So otherwise, I don't have to worry. What I'm trying to do is for simultaneously successful transmission, how far the receivers ought to be. That's all I'm trying. See, this condition directly doesn't tell you that how far the area occupied by each successful transmission. But if I can control this, then I can precisely tell you that each of two successful receivers have to be at least so far apart.
This is also.
There will be zero. How is it possible? Both are successful.
In XI, XK have to be far apart.
Okay. But that's what I'm asking. I'm asking in terms of Xi and Xj and Xk and Xi. Triangle inequality, all there is. Nothing more. So this is greater than Xj minus Xk minus XL. Is true. Clearly, right? No? Yes. What is this difference? XL minus XA. What am I controlling? This and this. What is the most trivial thing comes to mind? If you see a triangle inequality. What is triangle inequality tell you? That this ought to be smaller than, it's greater than some of these two, or this is smaller than some of these two. Smaller. That's all that. But now the communication being successful, it tells you something about something more. Which, what can I do more on this? The communication between I and J is successful, K and L is successful. Here, what's missing? Tell me. Something is missing. No, tell me what it is. Something wrong written on the board. Something is not clear. Ask me. There's no hesitate. There should be no reason to hesitate to ask. Are you okay with this inequality? Yes. Okay. Then
There should be a mod on the right side.
mod of all of this.
Yes. Right. It's fine. That would just give a stronger. It's fine.
Now look at this equation. This where is it coming from? My protocol model itself. So if I implant it here, what will happen? This is plus delta x something minus x minus yes. Okay, now at least you know that something can happen. Right? So what am I interested in? I'm interested in bounding the distance between two receivers in terms of xi minus xj and xk minus xl. I'm not yet completely done. I want something more. What more can I do? I can replace the roles of, what did I do? XL minus XG I did. This way. I can also think of this triangle. Correct? What will I get? I'll get another inequality of the same kind. Excel and if we do that, equal to that. I think what will be replaced here? And what will be replaced here? I'm just looking at this triangle. Just replacing the rows. First triangle that this triangle. Um, um, this this is a common. So if I do some circles, what will I get eventually? Left hand side is the same. Right hand side are two sums where I have interesting terms. This will be left hand side and just twice of Excel minus XG is greater than equal to how much? Delta times scale minus Excel. This adding them. So I'm actually able to get a lower bound on the distance between XL and XA in terms of the distance between XQ and XL and XI and XT. Now what would I do? What does it mean? That's all you have to do. Geometrically, what does it mean? That the distance between these 2 points is at least delta by 2 times this plus delta by 2 times this. So are there any non-overlapping regions you can identify?
Doesn't look right because says that XL minus XJ has to be some positive number. Right? But it can also be zero.
Yeah, the distance between them shrinks. They will also shrink. There's no constant setting there.
No, suppose all distances are 1, okay, it's all colinear.
Yeah.
Okay, suppose they are all colinear, XL, then to the unit distance. Okay,
To me,
XL.
XL, XK, XI, and XG.
So both the receivers are supposing a middle at the same point.
Okay.
When transmitter is to the left, when to the right.
This is not allowed, right? Not even allowed. The delta is exactly taking care of that. By the protocol model, that's not allowed. What is the protocol model? So as you push delta to 0, it will go to 0. What you are essentially asking is, can delta be 0? That's precisely why it is the control. Right? Is it clear what I'm saying? So what does it mean in terms of the distance between two receivers? I want geometric answer. Delta times the distance between this communication and delta is essentially the same. Delta by 2 times. See, now this is now one, not 1 plus delta. So this can be quite small. So it's just a function of delta, whatever delta you pick. But can you draw a picture which clearly tells us what is going on? which area has to be essentially disjoint. Or can contain at most one point. That's what really we care. We got a separation between the two receivers. That is important. So, let's redraw this. We'll try it. Extend. I want to play with this shaded this. Do not contain more than one point. What is that? What is that? What is the radius of this? What is the radius?
Delta times xl minus xl.
Delta by 2 times. This is between xi and xj. So I've got both of them. xl minus xk and xi minus xj. Clearly, it's exactly has one point. Here will be this one, which is all. Okay. So now we at least know that certain areas have exactly one receiver. How much is the total area? How much area is consumed by one? See, each successful communication, forget about the second one. If xi and xj are communicating, it's telling you that this much area is being occupied by them. How much is the total area? 1. Now can you tell me how many simultaneous transmissions can happen?
At most 1 divided by pi these things.
Pi r square, that area fine. But how much? In terms of n, what is it? I want the scaling in terms of n, right? The n points like in this unit square. So what is the first inequality will you write? That there are n by 2 pairs communicating simultaneously. So summation of delta by 2 times xi whole square. Pi r square. And how many I get this? Essentially all of them. There is no nothing going on really. All of them are trying to transmit at the same time. Each one is going to consume this much area. And it better be less than equal to. That's your real constraint that you figured out. Okay. Now tell me what is order wise, what does it look like? An idea belongs to the active set of. Start with this. Correct? Everyone is going to contribute so much to this. So you can ask, let me just make only one of them transmit. if everybody else is quiet, this guy can transmit at a very high rate possibly. But then the scaling is going to be very poor. If I don't allow sufficiently many nodes to transmit simultaneously, network wide, I'm not gaining enough. So there is a trade-off sitting here that you could say scheduling in such a way that only one node gets to transmit at the same time. But there are n of them. So your throughput is already down to 1 by n, which is pretty poor. So you can't do that. So anyway, we're looking for an upper bound. We will let this to be arbitrary. Whatever scheduling strategy you come up with at a particular time, this has to be true.
Are we not allowing hops?
We're not even counting. At least some one hop communication has to happen every time. How you route traffic is even higher level work. At any given snapshot of time, certain links have to get established. Each of those links, this much area is taken out. Total area is 1. So how many simultaneously I can do? Alternatively, try to compute the one. What is called the transport capacity. What transport capacity means is with meters per second. With meters per second. So I'm going to give. So if one bit is transported 1 meter, I'm going to count the multiplication of that as my quantity. If you are able to transport one bit 10 meters, I'm going to give you a credit of 10 meters. That's what it means, the bit meters. So in this time, if this is my communication model, how much is the bit rate? Xi and sigma g for all possible actives. Okay. You get it? The Xi is transmitted by Xi, that is successful. Over all possible actives. So this will be my bit meters. You can just multiply B1 entire. Doesn't matter. That is just fixed. Whenever I'm transmitting, I'm transmitting a disconnected. The number of bits is the same. What matters is how many meters I am actually going. So this distance between the successful transmitting pair is what is being counted as transport capacity. Can you bound this? Forget about bounding that directly. You bound this quantity. You should be counting the transport capacity directly. Just use Cauchy charts. That's all we do. So what is Cauchy chart tells us? Let's deal with the AR. See that much comments? Good. Something like indicator. Something I'm not filling up everything. Tell me what that is. This is this indicator that I is actually transmitting. Is this true? Some constant and method. You will remember Cauchy shorts. While I'm doing it, totally boundary size. That's it. So that's the theory. Oh, so which part I already have control over? I have control over this part, the square part. And how large can this be? There are total n nodes. At most n by 2 can be simultaneously activated because if n by 2 is transporting, n by 2 can be received. Total number is there. So this is at most n by 2. This is at most something times 1. It could be smaller than 1. How much is it? Just 1 by pi. 1 by square root pi delta. Make sure. Okay. Yeah. So this is at most 8. Where is it coming from? Okay, it is not important. Ready? What is going on? This quantity is at most n by 2. This quantity is at most 1 by delta square. Throwing away pi's. You could put pi wherever it would be. Oh, so what has happened? The transport capacity is getting as square root n. But this is across everywhere. Through the network. How much about per node? Can you count per node in this setup? Not really. Because I don't know each one. Some distance could be very large, some distance could be very small. What am I summing? I'm summing all the successful distances here. So they're not necessarily equal. So I can't simply say that I'll just divide it by. All I'm able to bound is that the overall bit meters I can transport to a network under the protocol model, at most square root n. Now we'll connect the SINR model and come back to this. That why does it even make sense to look at this? But is it clear what is going on? We looked at the protocol model. Protocol model precludes two receivers to be too close to each other. So each of those non-overlapping regions I will be able to count because all of them are transmitting or being successful at the same time. So that gives me an upper bound on the bit meters which are successfully transmitted. The Cauchy shorts is just Cauchy shorts. So now tell me how to connect the SINR model to the protocol. What does the SINR model tell us? The communication is successful. If greater than equal to beta, let's write it into this I is equal to plus summation x a to be greater than equal to beta. Now, what is the appropriate protocol model for this setting? If this has to be true, then you claim that the protocol model also has to be true. That there can't be a receiver very close, also a transmitter very close to XJ. In the distinction period, protocol model, a communication is successful if the receiver doesn't have any other transmitter in 1 plus delta multiplied by the distance from its own transmitter. Here, we not only but more than that, it is the signal power divided by the interference power. That should be it. Does this correspond to the question? When you write down a protocol model which exists, it should imply a particular protocol model. A particular means value of delta. I can drop some terms here. So I can always say that this is the scale greater than beta. Right? So this is not true, this is not true. And this implies that so drop everybody else except one. Just keep any one of them. What does it tell you? That d xi xj is smaller than what times b xj? This is only possible if you take 1 to the power 1 by alpha. That's correct. 1 by 2, 1 by beta to the power. Maybe 1 by beta to the power. Understand? So minus 1 I have to adjust because I want 1 plus delta. See, here I am only getting beta to the power 1 by alpha. In a protocol model, there was a 1 plus delta. So the new delta is nothing but beta to the power 1 by alpha. So this is nothing very different compared to the protocol model. So whatever result I am going to get from protocol model is just with a different delta, which is only dependent on beta. It doesn't depend on the network anyhow, neither the geometry nor the number of nodes.
It will be 1 by beta, right? 1 by beta is 1 by
But beta, it's in my notes.
minus.
Okay, perfect. Doesn't matter. Even if it is flipped, the constant. Okay, so how do I get my P of M from all of this? P, I mean, original goal was to get the per node throughput. All I've said is that my transport capacity is orders per root M. I've also said that SINR model corresponds to a particular protocol model. So what all I've said transport capacity for the protocol. SINR model. SINR protocol. Now question is what is T1 or n times. Give me any of this. Which part is not there? What is transport capacity counting? Bit meters. T of N has nothing to do with bit meters.
We should divide by average xi minus xj.
That is correct. And how much is, see, I'm picking randomly 2 nodes at a time. Not just xi minus xj. Essentially from source to the destination. That much successful communication is happening. But that is a constant. See, the unit area, no matter how many points you drop, you randomly picking 2 points, the average distance between them is just a constant. I'm not looking at the nearest neighbor or something. I'm just picking any 2 randomly chosen points. So what should my answer be? That n times T of n times the average distance should be equal to the transport capacity. So n times t is counting the total network throughput multiplied by the number of meters I'm moving.
Yes.
Right? So n times t of n times the average distance between chosen destination is roughly my transport capacity. I already know what transport capacity is square root n. My average distance is a constant. So t of n is square root n by n, which is 1 by square root. So you can't expect per node throughput to scale faster than 1 by square root n. So it's essentially going to 0, but at a rate not by n or anything else, but exactly at 1 by square root n. Is it clear what is going on?
How is the average distance constant?
What is the average distance between any two nodes randomly chosen in a unit area? N nodes. So let's just look at. Let's say W. Distance. Any randomly chosen. Yeah. Among n nodes whose locations in S1, then W times N times T of n is equal to 1 transport capacity. Okay. This I know is for the square root n. That is coming. W is a constant that you can simplify. It doesn't go. So n times Tn is usually order square root n. So T of n, so the per node throughput is actually going to go down at the rate 1 by square root n. Network wide, I'm increasing at the rate square root n. So this is what changed the landscape of wireless networks. This result essentially. The accompanying result in that paper showed that it's possible to achieve square root n by log n. They were not able to show that square root n also achievable. But a subsequent paper actually showed that in fact you can achieve square root n itself. That is what the difference is. Okay. So this limited time, I'll at least sketch out how to get to square root n. But at least whatever we have done is a very simple argument, completely geometric, took away everything out from the wireless part of it. All we did was we did a very simple protocol model with limited something very simply geometrical. That is where two receivers were able to simultaneously receive communication at a particular rate. Each of them have an exclusion zone around. Given that the total area is 1, you can only assign as many as n by 2 pairs. Simply, this is connected by. So this is, I think, the most important observation is that this is connected to this wire coefficients. If you don't see that, you'll never do this. So even though the most difficult step is the most simple here. This. So why would I start counting this? Only if I know that such a relationship. And that's a trivial relation, everybody knows. That's sometimes the simple observations make your life much worse. This is controllable because of the exclusion law. We are not used any sophisticated, we are not said anything about protocol, static scheduling protocol, what can happen, what will not. Simplest, the bare bones, give me the protocol model, this implies that the exclusion zones, that was sufficient to conclude the result. So not only the result is powerful, but the proof is not very difficult. The difficulty part in that paper was to actually show that square root n by log n is achievable. Because now you have to come up with a particular strategy. There's so many nodes, so many things are going to interfere with each other. How do you handle everything? But the proof I'm going to present is much clearer. Some of the results are not true, they fall from population theory, population on the square rate, but let's see what happens. So should I go to this or any things not near on the upper bound. That good? Okay. So we are going to tile it for S1, but like this. 45-degree lines. Okay. Get to it. This is how I'm going to do it. So each of this side is fixed. They might not look square for this. So this is. Now, done so badly. I'm going to put a vertical line and a vertical line. And I define this edge to be open if there is at least one point in that particular square. If there are any points in this S1, if a square contains a point, that particular line which is cutting this is defined to be open.
Both horizontal vertical.
Yes, that's all. Edge is open. It's this square. So I have to choose appropriately so that with high probability most of things are. So I'm going to use gory detail. I'll give you the broad idea, not exactly. This is the type. So this will result in. So now look at this horizontal and vertical edges. So essentially it's going to give you usual. So proper 45-degree lines, but really think of these edges as paths. Also think of this as a path. So this is why they have been an open path. Path for me always will be a left to right process. Similarly, there are top to bottom process. So this. So depending on S, control the number of left to right and top to bottom process. Is this clear what this means? So left to right means there is a connected path crossing this grid from left to right. And what top is the starting from the top. And I can control this via controlling the size of S. As I increase size, there is more and more probability with which an edge is open. So there is existence of more and more such paths. What I want is the following. I'm going to further divide. So think of this as a rectangle of the full grid. So this grid continues. And each rectangle, I want sufficiently many disjoint left to right paths. Disjoint means they don't have any common edge. Similarly, we have vertical triangles which have disjoint top to bottom paths. So these disjoint left-right paths are going to be called highways. So you're not traveling like Mumbai is reasonably good. So when you're going long distance, how do you travel? So there is between big cities, there is a big highway. You are somewhere in a small village, you somehow first connect here. Then there's another highway cutting another highway. And this is where you want to go. So you get onto the nearest highway, you travel as far as you can, and then you move on to the perpendicular highway, and you get off, and then you get. That is precisely what the policy was. So this is one particular strategy which will get used for it. There are many other ways you can do it. Upper one tells me I can't do any better. This disjoint left-right paths are going to be my horizontal highways. Why disjoint is important? Because I'm going to assign certain amount of traffic to them, and because they don't overlap, I don't have to worry about it. Similarly, I have top to bottom. So any node which wants to communicate with anybody else. So this is what is going to happen. A random source is going to choose a random destination. I will go on to my nearest highway. So think of this as using this path for travel. And then there is another. So you go as far as, so I'm going to draw squiggly for a top to bottom crossing. Go to the nearest vertical highway on this horizontal highway, and then move from this to this. You go up and then you transfer. That's precisely my shift protocol. Is the protocol clear? I'm going to define rectangles of particular height, which will tell me that there are so many disjoint. So rectangle choices have to be made appropriately. I already made a choice of S appropriately, so that there are sufficiently many disjoint, both left-right crossings and top to bottom. I choose rectangles so that each of these rectangles contains sufficiently many of such paths. All of this will be precisely to get the square root and result. Essentially get the range that what is going on. Now tell me which parameter or which part of the scheduling controls the throughput. Eventually I have to worry about throughput. What do I want? That each source destination should be able to communicate at the rate of 1 by square root n. That's all I want to care about. So what is sufficient to show that?
Such parts where exist.
So that you know, not shown in here, but depending on S, this you can show. That is just usual calculation theory, which you are not gone into. But that is guaranteed by already existing results. I don't have to worry about it. And the point is disjoint. If they are overlapping, so then you should just show that there are sufficiently many top bottom crossings and left right crossing. This doesn't work. You also have to insist that are disjoint. So think of them as like optical fiber cables which are disjoint. Each of them can carry same amount of traffic. If I have just one of them which is crossing, so think of 10 optical fiber cables, but eventually joining into a single router. The single router will limit everything. Here, what we are saying is they are disjoint also. So that is the important part. So each of these have to be chosen appropriately so that there are sufficiently many disjoint paths sitting inside each rectangle. But that's not very difficult. Once you know the scaling of how many such paths exist, it gives you a natural choice of that. But think about what is the protocol. This is a protocol. This is scheduling strategy. What is sufficient to show so that each transmitter receiver can communicate at the rate 1 by square root n. Is the strategy clear? Highways are nothing but left-right crossings or top-bottom crossings, which are disjoint. Every node will get first onto its nearest horizontal highway and exit at the nearest vertical highway. So each horizontal highway is dedicated for who? Only people lying in that rectangle or some part of that rectangle. So all you have to worry about is how many people are there in each some part of the rectangle, because they are the ones who are going to share the bit pipe, which is the horizontal highway. And what is the throughput of the horizontal highway? Two things you have to control. That how many people will share that horizontal highway, and what is the throughput of the horizontal highway itself. So think about both. Can you argue that it is roughly 1 by square root and for each node? If it's not clear, ask me what is not clear, then I will tell you. So first try to establish that the throughput on each highway is a constant. Something very similar to what we did last time. So tell me a scheduling strategy which will ensure that each highway can carry a constant amount of traffic. Which was whatever we did last time. How did we control the interference? We made sure that people close by did not transmit. By coloring, you can use exactly the same idea. So think of any one particular node on the highway. All I want to say is that, so suppose this guy, somebody is sitting on this highway. That's what it means, that this contains a particular point. The highway is not a straight line. It's just that this particular physical point is giving rise to this edge being open. So this point is actually not going to behave like a relay. We're going to transfer. So if he has to be successful on this particular path, what has to happen? The interference has to come from sufficiently far off. And how can I control that? Exactly the same way like last time. I can make sure that the interferers are sufficiently far. Let's say this guy is allowed to transfer, this guy is allowed to transfer, this guy is allowed to transfer. And I can, in this particular way, I can control this by making sure that it like using is where different times to ask. So when I'm transmitting, T square name of the non-nodal transmitter. Everybody else. So just think of it as a repeated pattern. If I'm transmitting, none of my K square neighbors are going to transmit. And K can be a constant to show that a constant amount of throughput is possible over this particular from here to here. That's all I care. You can, if you want, you can see it in the book, or you can convince me that it's exactly similar to what we did back. Right. What we are preventing is not everybody in the adjacent nodes are at adjacent square allowed. So my nearest transmitter is going to be K square distance, K square times the size of this edge. And that I can control. To say that I can transmit from this node to this node. Think of this as actually the highway. These nodes are physical entities, highways are abstract entities. The connection on highway essentially means that this node is transmitting to this node. If you follow such a strategy, you can show that this node is transmitting to its neighbor at a constant rate. And that will establish that each of these highways, the K square is a constant. The constant could be very large, in which case the throughput is 1 by K square. But I don't care about all that. It's not changing with n is what I care. So the throughput is a function of 1 by K square. But that all of that is pushed under the carpet as a constant. It's not decreasing with n is all I care. Okay, so throughput on each of the horizontal highways as well as the vertical highways can be shown to be roughly 1 by K square, where K square is the constant. And where the K comes from, K is essentially the summation of the interference, which is far away, so the sum series sum converges. So that establishes that each of these highways can carry a given amount of current. Now, how many people are going to share that with us? Can you give me an upper bound on how many people are going to share? So I've not specified everything, but at least give me, using your Chernow bound arguments, how many people you think are going to be sharing each of these paths while making sure everything else also works out. So what have we said for so far? That the left-right path on a highway can carry order 1 element. Now, I will be done if I can show that at most square root 10 people are going to share this. That is all I have to show. no more than square root n. So why square root n is the question?
How many highways do we have?
That will depend on how you choose S. So I'm not, I'm at loss here because if I were to go, I'll go way overboard. But get the big picture that the number of highways will depend on how large the N is. And appropriately I'm choosing number of rectangles so that the number of sub rectangles, so I also want something like a sub rectangle. All of these are size square root n. Yeah. So side S external. S is of order square root. So that's the first starting point. Now this will tell you that the number, what is the probability that at least, so how many roughly number of points you should find in the square root n. And n points in unit area. My box is of size 1 by n. So constant number. The size is just 1 by square root n. So the area is order 1. So constant number of nodes you should be able to find. If it's now large enough, you get the too high probability, the sufficiently mitigated. You can throw in a log n wherever you want. That's nothing. Depending on tau, I have so many left, right, and top bottom crossing. Then I'm going to go and look at rectangles. Simply there are sufficiently many left, right, and top bottom crossing. So I'm going to subdivide the rectangle so that in each subdivision there is at least one path, which is going this way and crossing it. All you have to argue is the number of people who are sharing this order. That's all. So 3 steps ahead. First, you look at the square grid coming out of your unit square, making sure that there is sufficient probability with which each edge is open, and there are sufficiently many left-right crossings and top-bottom crossings. They will serve as my highways. Each highway, the critical step also shows that each highway you can manage an order 1 throughput. And then the number of people sharing that line. Because the subdivision on this rectangle, which I am going to show, will exact the one path will be dedicated to all the nodes lying in this. All the nodes lying in that, with smaller than that. And that you have to show that is atmospheric. So overall, I have order 1 communication happening over this particular value. That's why n people are going to share it. So each one is going to get 1 by. It's a much simpler proof than the original. But still, I'm not giving you the full detail. Actually, a couple of pages in the book. They just have to do a proper bookkeeping. Each size has to be checked out properly. But as long as the basic idea is clear, you can read up the details. So tell me if the idea is not clear. Then I can help you. So this is a key step that you can actually show that each highway can carry a constant amount of length. It's not obvious why that should happen. But that is essentially by making sure that no profile do not conflict and then probability of the better. Exactly like last. Like you can see simultaneously transmitting nodes sufficiently far apart. Essentially control the minimum interval. The minimum is exactly the maximum. The nearest neighbor who will give you the interference is if it's control, then you can show that the series converges. That's the first significant. The second risk level is that each highway is shared by only square root n number. Good. Yeah, details are not. Once you have the idea, details are not. But this took a while. The original proof will be short. Square root n over. That proof is also very important. It started finding also. If you've not heard of this word, something to do with Warner tessellation of a sphere. That's what they tried. And that was very difficult. Okay, so let me stop here.